Welcome to Bufferbloat, shedding some light on this dark topic by demonstration. I'm Jim Geddes, your host. I hope the following demonstrations will help you understand Bufferbloat and its devastating consequences. Thankfully, you can reduce the pain when Bufferbloat causes in your house. Buffers are essential to absorb bursts of packets that often occur in a network when fast network links meet slower links. Empty buffers are dark. They impose no delay. It's only when they fill that the delay starts to occur. But how much buffering is enough? By design, TCP tries to run as fast as it can given the lowest bandwidth link it has in the network path between machines. Any long-lived TCP transfer will therefore fill any size buffers in a device just before the bottleneck in a path. I will demonstrate typical home buffer bloat using my home network. There are two common bottleneck links in my home. The broadband connection, on this diagram that's located right here, and my Wi-Fi connection. The bottleneck can be in a different link in a different direction and can move as the bandwidth available changes. Depending on the direction data is moving, there are therefore 4 locations where buffer queues may grow in these demonstrations. Your laptop or device in the upstream direction, your home router, your broadband connection itself in the equipment in your house, or in your ISP's broadband equipment. My service is typical for today's broadband service, and I have over 1 second of delay. To demonstrate buffer bloat, we'll use Google Search, which is carefully optimized for speed, using a typical broadband connection, as shown by the ICSI Nettalyzer data. We will run 3 tests. During the first test, we just run the benchmark on a completely idle connection. As you can see, the benchmark runs very fast, visiting Google Search 5 times. The results are on the screen. The second and third tests add a single file copy upstream to the identical benchmark, which is downloading web pages. How fast do you expect this test to run? Just as fast? Half as fast? I let the copy run for 10 to 20 seconds to both fill the buffers and to overcome any speed boost that the ISP may give me, such as Comcast does with Power Boost. The file copy is from my laptop to a server on the internet. This operation is just like uploading a video to YouTube or Vimeo. Sending an email with large images attached or a video attached is another example. A third example might be backing up your files to a remote backup service. With that single competing outbound copy, you can see Google performance is now glacial, through no fault of Google. You might have predicted that performance should be nearly as fast as the first test, but it's not. It's radically slower. Even experts often overlook the damage to downloading caused by filling the bloated buffers in the upstream direction. Trying to use VoIP over this link is like talking to someone halfway to the moon. This really is, the internet is slow today, Daddy, as my family kept telling me. As you'll see from the benchmark results shortly on the screen, the 5 visits to Google Search now take 10 to 15 times longer than they did during the first test. For the third test, we'll insert an artificial bottleneck that has little buffering by using the so-called QoS features of many home routers, moving the bottleneck from the bloated broadband link into a location in the home router with little buffering. To ensure that the bloated buffers in the broadband link never fill, I am setting the bandwidth to 70% of the ISP's provisioned speed. We run the benchmark again while the file copy continues. We are now close to the speed of the first test, despite the bandwidth reduction and the simultaneous copy, achieving performance about what you might have originally predicted, or maybe even better performance given the bandwidth reduction and the copy. The internet is slow today phenomena is gone. Reducing our bandwidth by 40% sped up the service under load by a factor of 10. Anyone using a link can destroy performance for themselves or for anyone also using that link when it's the bottleneck link. Remember, this demonstration was on a link of typical buffer bloat. Bandwidth and speed are only vaguely related, as Stuart Cheshire explains in It's the Latency, Stupid. Which internet service would you prefer to share with your family or use at a hotel or a conference? One with buffer bloat or service of the same bandwidth without buffer bloat. I think this demonstration makes it very clear. Most people are still using 802.11g Wi-Fi. Its 54 MHz is a signaling rate. You can actually transfer only a little more than 20 megabits per second of actual data over an 802.11g link. Since most people's broadband service is in the 10 to 20 megabits per second range, and both broadband and wireless bandwidth changes with time, the bottlenecks often shift back and forth quickly between the broadband link and the Wi-Fi link. For this demonstration, I forced my home router to only use 802.11g, and as I now have downloaded a download bandwidth of 50 megabits a second in the second demonstration, the bottleneck is firmly in the home router. There is no competing traffic. This is as good as it gets. Again, we'll visit google.com 5 times and record the result. The first test is with no competing traffic with speedy disabled. In this case, I'll demonstrate buffer bloat induced by a different machine rather than this laptop. This is Daddy doing in the rest of his house. The second test again visits Google 5 times while copying large files from my server at MIT. Downloading a movie to disk or copying a large software package such as a Linux ISO image will have the same effect. Your mileage will vary dramatically. If you are far from your router, the effective size and time of a buffer can be multiplied from this demo. Buffering differs between routers quite dramatically. A simple bandwidth test won't show this difference in behavior. As you can see, the page load time increased quite dramatically, at least a factor of 3 or more. On top of all of these problems, even worse, routine web browsing is inducing transient buffer bloat of order fractions of a second, which can play havoc on real-time applications such as voice over IP or Skype. Let's remind ourselves of triggers. In short, anything that saturates a link. It takes a few seconds for TCP to fill these insane buffers. Thereafter, they operate nearly full continuously. But buffer bloat is present to varying degrees in equipment all over the internet, including our servers, desktops, laptops, cell phones, and many routers and switches in between. Until we fix buffer bloat, our networks will fall off performance cliffs rather than degrading smoothly under load as they should. We have a first-class mess on our hands throughout the internet. Today's demonstration was using the home broadband part of the mess about which we know the most today. But look everywhere for buffer bloat. Help in whatever way you can. At the least, you can help yourself and others around you while the buffer bloat problem gets solved. It's grown for over a decade. Conquering buffer bloat may take another decade. For more information, you can read the communications of the ACM articles that have appeared online at the ACMQ website. Thank you for your interest.